Hello everyone, Science Club heartily welcomes you all to the talk on symmetry titled Beauty in the Broken Things. Symmetry is at the heart of the universe. Even Kepler tried to impose his notion of symmetry on the motion of the planet. Einstein was the first who thought of the symmetry as a fundamental feature of nature. From Noether's theorem to the exciting world of atomic local symmetries being revealed by modern physics. But if symmetries are so pervasive and influential in the world, why do we see so many asymmetries and chaos in real world? To understand this, we have today's speaker, Dr. Arun Thalapillil. Dr. Arun is currently working as an assistant professor at IISER Pune in the domain of high energy physics. His contributions are in the field of quantum field theory and astroparticle physics. He has completed his undergraduate studies from BITS planning in electrical and went on to do graduate studies at Enrico Fermi Institute, University of Chicago, and was a postdoc fellow at New High Energy Theory Center at Rutgers University. He is the best ongoing student at the Department of Physics, BITS Planning, Young Science Fellow at Indian Institute of Science, Bangalore, and scored 4th rank in the Regional Maths Olympiad. We welcome you, sir, for the today's talk. Few guidelines before we begin the talk. It would be nice if you can get the queries on the talk. Feel free to ask them by unmuting yourself or put them in the chat box. A small poll of audience who are watching live stream video can put their queries in the live YouTube chat box. We welcome you, sir.
Thank you very much. Am I, just to make sure, am I audible to everyone? Am I visible as well?
Yes, sir.
Okay, so thank you for the very kind introduction. That was actually more formal than I expected, and I think she has already set the expectations high, and I hope I'll be able to fulfill this. So let me start by sharing the screen. And please let me know if my screen is visible. Is the slide visible?
Yes, sir.
Okay. Yes. So before I begin, I just want to mention that I've thought of this as an informal chat. So please feel free to interrupt me at any time, ask questions in between, and so on. Okay. So please consider this as an informal chat rather than me talking and you listening, and then there is so please be very informal. Please ask me any questions, interrupt me in between, and I hope you'll feel sufficiently comfortable to do that. So going with the theme of this beautiful theme that the Science Club has envisioned, symmetries in various fields in sciences and humanities and arts, I thought I would talk a little bit about symmetries as they apply to the fundamental laws in physics. Okay, the fundamental laws which govern our universe, with a slight twist. What I thought is, as beautiful and as remarkable as what is really remarkable, even more remarkable, is the fact that many times, oftentimes, it's precisely the way in which symmetries are broken. Okay, the unique ways in which they are broken that actually leads to really interesting things. Okay, and I hope by the end of this talk, I would be able to impart this really remarkable idea to you. Okay, now you see a picture of a broken pot in the first slide. Now, in the Japanese tradition, there is a philosophy called wabi-sabi. Okay, there isn't a very good literal translation in English, but roughly wabi-sabi is a philosophy which looks for beauty in broken things or beauty in imperfections. Okay, beauty. One manifestation of the Japanese art form called kintsugi. Okay, kintsugi is basically you join broken pottery using lacquer, mixed with gold or silver or platinum particles. Okay, as you can see, there are inlays golden in color. Okay, so kintsugi is one of the physical realization of this Japanese philosophy called wabi sabi, and I've always been fascinated by it. That and we can get into a philosophical discussion about it is actually all the richness of even life comes from actually the imperfections. In some ways, maybe a symmetric life even might be something boring. And I want to say something about how a similar thing is there even in the fundamental laws. Okay, so this is what I'm planning to do. Just to make sure that I'm just not just audible, the screen is visible to everyone, right?
Yes, sir.
Yes, sir, your
Okay,
screen is
okay.
visible.
So okay, very good. Okay, so we are all born with some even like intrinsic notion of symmetry and association of symmetry with beauty. Like on the top left hand side, this is a picture of the Alhambra in Spain, and you can see this really beautiful wall art with beautiful carvings on them, and even without knowing any formal notions of symmetry or groups or anything, any person can appreciate the beauty of this. On the right hand side, you have a tiling pattern, which is a if you were to do a translate any element of it by some finite distance upwards or to the right, you'll see that you'll find a similar pattern. So this is called a periodic tiling, and tiling refers to the fact that basically such a pattern can fill all of the Euclidean plane. Okay, in that sense. So again, here there is on the left you see a sculpture. Okay, again. There is some notion of there is some pattern or there is some symmetry to this sculpture, which again is visible. Some symmetries can be it needn't also be of a visual nature. It can be of a auditory nature. Like for example, this is the sheet music for Ode to the Joy by Ludwig van Beethoven, and the symphony also has some particular structure to it. Like, symphony many times is written in what is called the sonata form, which is a particular pattern. So some symmetries are also of this nature that, it's not exactly visual, but trust me, if you hear the symphony or a beautiful raga rendered, you would be able to appreciate it. Now, it's also very strongly believed and suggested that our notion of human beauty also has something to do with symmetry. In fact, this picture on the lower right-hand side do not belong to any man or woman alive. In fact, it is a completely computer-generated image of, a computer was asked to guess what a notion of beauty might be like, and this is one interpretation of at least as far as this computer is concerned, what an attractive face might look like. And here again, some of the notions used by the computer was based on symmetry. Okay, but as I hope I will soon convince you, things are a little bit more interesting and richer, thankfully. Okay, than just this notion that only symmetric things are beautiful or something. I think that is in some sense too naive. Okay, of course, there are also patterns and symmetries in nature. In the among flora and fauna, there are beautiful patterns, whether it's the stripes of a tiger or the patterns on a beautiful bird. So there are symmetries in nature, and what is shown here is like a morpho butterfly, which has this very beautiful iridescent wings. On the right is a spiral galaxy, not the Milky Way, but a galaxy which is kind of similar to the galaxy we live in, again, you can see that there is a kind of a pattern, there is kind of a symmetry, and you can even appreciate it from an artistic point of view. At the center is a diffraction pattern formed by laser. So essentially, if you were to send laser through a aperture, a small hole, you will actually see a smooth flowing river. Again, has a pattern built into it, even without knowing the underlying physical law or Navier-Stokes equation. Anybody who has ever spent any amount of time near a water body can appreciate the calm, relaxing effect of a laminar flow. Okay, on the right, these are what are called Abrikosov lattices. This occurs in superfluids and superconductors. Superconductors are basically things which can basically conduct electricity with zero resistance. Now, in a particular type of superconductor, the detail is not important, something called type 2 superconductor. If you were to pass a magnetic field through it, it forms these beautiful patterns in the superconductor. Or if you were to take a superfluid, roughly speaking, is something which has zero viscosity, something like liquid helium. And if you were to stir liquid helium or Bose-Einstein condensate, for example, you will actually see that certain vortices form in this, just like whirlpools in a bathtub or in a sink, but they have a very, very well-defined pattern, and these are all described by very beautiful physics. Okay, so there are patterns in nature apart from man-made or slightly more subjective patterns, which we are also familiar with. But there are also subtler symmetries, as alluded to also in that nice introductory video we all watched. Some of these subtler symmetries, see, earlier we looked at what we called a periodic tiling on the top right. But you could also have more interesting tiling patterns. For example, what is shown on the left is what is called Penrose tiling, after Roger Penrose, who recently won the work on the singularity theorems, black hole formation and so on. So here, in periodic tiling, I said that there is kind of a translational symmetry. If you were to translate that any single segment by a finite distance, it overlaps with a similar unit. Here, if you were to translate it, you can convince yourself very quickly that this tiling does not have a translational symmetry. Okay, but it does have some other symmetry. Okay, in fact, it has what is called a reflection symmetry. If you reflect it about certain axes, you get a similar pattern. In fact, it has, in addition to that, something called a five-fold symmetry. What a five-fold symmetry means is, if you were to rotate it by multiples of 2 pi by 5, 180 degrees by 5, the pattern would go back to itself. So just like a square has a four-fold symmetry in that sense. Okay, 2 pi by 4. So similarly, this has a five-fold symmetry. But this is actually as you can just see, it's more interesting than just a periodic tiling. Another place where there is a pattern, but it is actually much richer. In fact, this is one of the outstanding problems in classical physics, is the problem of turbulence. We talked about laminar flow for a smoothly flowing river, where things were moving slow and there was a pattern. But if in some sense things are fast moving, you enter a regime called turbulence. And in turbulence, the patterns are actually not very explicit. There is a pattern. In fact, there are beautiful patterns here, but you might have to see a little or think a little bit more to appreciate this pattern. Okay. Also in music, we talked about symphony usually having some scale or some sonata form, but there are also musical creations. For example, pioneer. A very famous composer, Arnold Schoenberg, called atonal music. Atonal music just means that, usually in compositions, there is an idea that, okay, there is a central or dominant tone or a scale, and you kind of base your music around that scale. Okay, maybe C sharp, C major scale or D minor scale or something like that. Atonal music completely abandoned this idea. Okay, there is no, in some sense, a tonal center, and again here, some people call it noise, some people call it beauty. Again, some training or some perspective, but it's a more subtler kind of pattern. Now, coming to symmetries in physics, okay, the symmetries in physics are also subtle in a different way. What is shown on the left are Maxwell's equations. Now, most of you might know them in a different form, like from school, we learned it in some integral form. But if you have not even seen it in this form, you will see it in like a few months or a semester at isopony. Okay, but trust me that these are just Maxwell's equations. Okay. Now, Maxwell's equations have a symmetry. What kind of a symmetry? Again, it's a subtler kind of symmetry. Here, the symmetry has to do with the fact that you can do some variable transformations, as in you can take the electric field and magnetic field to another frame of reference in some sense. You can define, that gradient is basically like a derivative. X goes to X prime, E goes to E prime, B goes to B prime. You'll see T goes to T prime. You'll see that the form of these equations remain the same. Okay. Technically speaking, there is Lorentz invariance. Okay, there is they are symmetric under Lorentz transformations. Okay, or they change they change covariantly under Lorentz transformation. So there is a subtler kind of symmetry under a transformation which is built into Maxwell's equations already. Okay, in fact, this was one of the motivations for Einstein to actually think about special relativity earlier in the early 20th century. What is shown on the right are similar equations for gravity, a theory which describes gravity called general relativity, as maybe many of you would have heard about. Now, it's not important what any of these terms mean, but the important thing is, just like we have Maxwell's equations, these were equations for the fields, the electric and magnetic fields. Similarly, these are also field equations, except that the field is like the gravitational field, okay, loosely speaking. Now, these Einstein equations, okay, which are the analogs of Maxwell's equations for gravity in some sense, loosely speaking, also have a symmetry here. Okay, in some sense, it's the symmetry of invariance under coordinate transformations. Okay, the physics doesn't care about what coordinates you work under, essentially. Okay, so even the field equations have a subtler kind of mathematical symmetry. Then there is another class of symmetry, which is that if you look at the subatomic particles, you see this octagonal structure, right? You're familiar with N and P, which is the neutron and the proton. There are also other particles, okay? And you see that even for N and P, neutron and proton, there is some UUD, DUD. So the neutron and proton are bound states of what are called quarks. Okay, so proton is actually a bound state of 2 up quarks and a down quark. That is what is being denoted by UUD. Similarly, a neutron is a bound state of 3 quarks, down, down, and up. These names, down, up, strange, charm. These are the names of quarks, okay? But these are just names, okay? They were these are whimsical names, but given by Gelman in his wisdom. But they're just names, okay? Just to denote them. So even for these particles, they kind of form certain families. For example, here you can put them in the form of a octagon in a certain sense. Again, the exact details are not important for this talk, but I just want you to appreciate that in a certain sense, the proton and the sigma plus have some symmetry with them, like both are positively charged. If you look at the other off diagonal particle, the neutron, the sigma zero, and the other one, the Greek alphabet, which I forget, they have again a charge zero. Okay. Similarly, the sigma minus and the other one. So the point is that again, there are more subtler kinds of symmetries in the physical laws or mathematical laws. Okay, so these are also subtler symmetries in that sense. And just to emphasize, just to give you a very small flavor of what kind of symmetry we are talking about in the earlier case, some of these symmetries in the physical laws have to are very intimately related to invariance. All of you know this. Okay, let's say you have a vector in the xy plane, okay, of length L. So it's x coordinate, y coordinate. The vector is starting from the origin, and the tip of this vector has coordinates x and y. You know from analytical geometry, or you know how to calculate the length of this vector, some square root of x square plus y square. Now assume you are not measuring the length of this vector in the x and y coordinate, but you want to measure it in some coordinate axis which is rotated with respect to the x and y axis. Let's call it, I don't know, x prime and y prime, okay, which is shown by the blue coordinate axes. Now the tip of the vector is no longer at x and y, but to the new coordinate axis, it's at x a bar and y a bar. You can again calculate the length of the vector, and almost trivially, just geometrically, you can convince yourself that it should not matter whether you measure it in the xy coordinate or whether you measured the length or calculated the length in the x prime y prime coordinate, which was rotated. The length is the same. So this is a simple example of invariance. The length of the vector under rotations is invariant. Now, some of the subtler symmetries we were talking about earlier are also related to similar invariances, some generalized form of invariances. Okay, and so this is the basic idea of where some of these symmetries come from. It's many times intrinsically related to invariances. Okay, and as very beautifully put in the video, a towering figure in this understanding of symmetry, how symmetries are related to what I call, conserved quantities and so on, is M.E. Noether. In fact, I should say when general relativity was discovered or invented, there were two towering figures who were actually competing for a truly relativistic theory of gravity. One was Hilbert, who was a giant in mathematics. The other was Einstein, who was already in physicist in physics. Sorry, that's a tautology, an eminent physicist, because he was already kind of famous for special relativity, and general relativity came much later in the 1920s. Kind of, they were competing for a theory of gravity, and one of the things, even after Einstein, in some sense, got general relativity, was to understand the nature of conserved quantities in general relativity. And neither Hilbert nor Einstein had a very good notion how to do it. And to compress a lot of interesting history, I would say that it was M.E. Noether who actually clarified nature of symmetries, how the beautiful way in which various transformational invariances are related to conserved quantities, how symmetries are related to conserved quantities, and so on. Okay, and it's a travesty that her accomplishments were actually not recognized because it was a different era. There was a lot of bias against women scientists. You know, and so this was a very unfortunate and a travesty of justice. So I just wanted to mention this, that you can't talk about symmetries without talking about a mean author. Okay. Now, if you look out into the night sky, perhaps with a very powerful telescope, this is what you would see. This is an image from the Hubble Space Telescope. This is called the ultra deep field view. This is in some way the out into the universe. So what you're seeing on your screen, some of these small specks, even the tiniest speck, is like a full galaxy. Okay, and this is the deepest into space we have been able to look. Okay, you can see that there is a lot of pattern. There's a lot of stuff here, right? And I want you to appreciate the profoundness of this image. We are actually, the distances are immense. Okay, the kind of distances we are talking about, light, which is as far as our common perceptions are concerned, almost travels instantaneously. From some of these objects takes billions and billions of years. Okay, so these are really far off objects. The distances involved are astronomical. And even you should think we see kind of a spiral galaxy there. Each galaxy on an average contains things like 100 billion stars. Our Milky Way has about 100 billion stars. Our sun is one of these. Okay, there are at least 100 billion galaxies out there. So it just gives you it's a very humbling experience to look out and and realize that yes, it's also inspirational that we are actually part of something really grand, but it's also a very humbling experience, compared to nature, compared to universe, how small we are. Okay, but the point is, it's a very interesting world out there. You don't need to necessarily look at a galaxy. You can look out your window and you can see structures, right? Trees, birds, the wind, rain, etc. Okay. Now, all the stuff which we see, okay, let me put it in quotes. They're all composed of the things we can see in quotes. So they're all composed of certain subatomic particles. Okay. So let me just spend a minute just to give you a lightning review of the subatomic particles we know about and the fundamental interactions. So just like we have the periodic table for elements, okay, for subatomic particles, which are like the fundamental particles we know of in the universe, there is a periodic table, kind of like a periodic table. That is what is shown on the left-hand side. So, as we said, these things like U, D, they are just quarks. Up quark, down quark. E is electron, which again you're familiar with. You might have heard of neutrinos, that is nu sub E. And there are different kinds of neutrinos, nu sub E, nu sub mu, muon neutrino. There is something called a muon, which is just like the electron, negatively charged. It has similar quantum numbers, except is much heavier. Okay, particle physicists like to measure it in units of electron volt, and you can see electron is in those units 0.5 mega electron volt. Muon is like 100 times more massive, roughly, or 200 times more massive. Okay, then there are what are called force carriers. Okay, the gamma, which is the photon. So in the modern understanding of fundamental forces, so we know that as far as we know currently, there are 4 fundamental forces. Electromagnetism, okay, gravity, both of which we are relatively familiar with. We study their theories in school, Newton's theory of gravity, which is subsumed by general relativity and so on. There are other 2 forces also, which again called the weak nuclear force, which is responsible for things like radioactive decay. There is another one called the strong nuclear force, which is responsible for keeping the nuclei together, the protons and neutrons together, or even, we talked about how the proton is a bound state of quarks, which is what is shown on the right. So these are all bound. What is shown on the right are all composite particles, or more correctly, bound states composed of these elementary particles: proton, neutron, there is antiproton, and then some other, pi plus, K0. Okay, there's a whole zoo of bound states. Okay. Now, the force carriers, the reason it's important is because in the current way we understand the fundamental interactions, they're kind of mediated by these force carriers. So when I say that like charges repel electromagnetically, the notion is that there is actually a photon, it's actually a virtual photon, but it's not important, which propagates between them and which kind of mediates this interaction, attraction or repulsion. Okay. Similarly for the others, when you say there's beta decay, radioactive decay, they're actually mediated by the Z and W bosons. Okay, so this is kind of our periodic table for subatomic particles, and using these elementary particles, you can also have bound states. Was there a question?
Excuse me, sir.
Yeah.
Sir, where is the Higgs boson in this?
Yeah, so I deliberately omitted it for a reason, as you will see, so that I can build up a story. Thank you for the question.
Okay.
Okay. Yes, there is also another particle or field, more precisely, which we'll come to. Okay. But here, I want to make a point. Okay. So thank you for that question. Okay. So what I'm trying to say is everything we see around us, this desk, my coffee mug, the trees, the birds, all are made of atoms, and atoms are made of proton, neutrons, and electrons. Okay, which is actually only one part of let me call it the subatomic periodic table. Okay, but you look out into the universe in astrophysical observer, or if you there is a scanning technique called PET scans, which is called positron emission tomography. You want to kind of actively monitor the brain. Okay, you would maybe do a PET scan. So positron is an antiparticle of the electron. They don't occur ubiquitously, but things like antiprotons or positrons, these are now regularly produced by man in either hospitals or even you can also see some of these other particles in cosmic rays. But the point is, things we see, things we observe are mostly particles from this subatomic periodic table, as I would put it. Okay. Now, there are certain symmetries, fundamental symmetries, okay, which govern these interactions, govern the underlying physical theory behind these fundamental interactions. Okay, the fundamental interactions are all based on a quantum field theory. Gravity, it's unclear how to unify it with the principles of quantum mechanics, but at least in the weak gravity limit, there is a something like a quantum field theory, even for weak gravity. Okay, there's just a technical point, but the point is that you can explain what a quantum field theory means currently is not important, but it's some mechanics or some quantum mechanics or Newton's gravity. It's some theory which helps you make very precise theoretical predictions, and some of these predictions can be tested experimentally to 15 or 16 decimal places. Some of these theories are often referred to as the most perfect theories created by man. Okay, and there are symmetries which govern these interactions. One of them is a particle-antiparticle symmetry. Okay, which was first appreciated by Dirac. In fact, it was Dirac who, in fact, first predicted that for every particle there should be a corresponding antiparticle. What is the difference between a particle and an antiparticle? They have the same mass, but all the quantum numbers are flipped. For example, electron has a negative charge. a positron, which is antiparticle of the electron, will have a positive charge. Okay. Similarly, every particle has antiparticle. Now, it may happen that certain particles, their antiparticle is a particle itself. Like for example, for a photon, its antiparticle is a photon itself. Okay, but people notice that there is a symmetry, like the generalization of electrodynamics, Maxwell electrodynamics, is called quantum electrodynamics. There is a very nice particle-antiparticles, but it was soon realized that this symmetry is so it's a little bit like Star Wars. There's a dark side of the force, there is a light side of the force. In some sense, they are counterparts, they're two sides of the same coin. Okay, this particular antiparticle symmetry is a little bit like Darth Vader and Luke Skywalker. Okay, and one of the first indications that something is slightly amiss is the fact that there is more matter than antimatter in the universe. We are all made of matter. Okay. Now I said, okay, we produce positrons, we produce antiprotons. That's true. But what we mean here is that you look out into the universe, you see matter. Okay. They can be produced as secondary particles. Okay. Maybe the sun produced coronal ejection, and then, through produce positron. That kind of thing is possible. Or in a neutron star or a pulsar, it gives out a stream of positrons. But you don't see, antimatter in any quantity which is even comparable to matter. So this is the first indication that there is something amiss, and the fact that the particle and antiparticle symmetry is violated. Okay. Now, there was another symmetry which was observed for fundamental interactions, which was symmetry under parity. So what parity means, to simply say, is if you have the spin of elementary particle and there is a momenta, if the spin and the momenta are in the same direction, we'll call it some notion of this right-handed rule, which you're familiar from electrodynamics. If the spin is in the opposite direction, you would call it left-handed. Okay. So Wigner noticed that, again, things like electrodynamics, quantum electrodynamics, or even other seem to have this symmetry. Left-handed electron has all the same interactions, apparently, as the right-handed electron. Okay, this was a notion earlier in the 20th century. But very interestingly, it was soon observed through very beautiful experiments by C.S. Wu that actually even parity symmetry is broken. So essentially, what she did through a very difficult and careful experiment, a very beautiful experiment, is basically she looked at how radioactive cobalt decays. Okay, and again, the technical details are not important, but if there was a mirror symmetry, as shown on the left-hand side, okay, maybe some of you know about axial vectors and polar vectors. Axial vectors under r vector going to minus r vector kind of transformations. Axial vectors don't flip sign because axial vectors are built up of other vectors. Like, if a vector is built up of a vector cross b vector, under parity, maybe a vector will also change sign, b vector will also change sign, but then a vector cross b vector doesn't change sign. Axial vectors are kind of vectors like that. Okay, things like angular momentum and so on. Polar vectors are in some sense more familiar vectors. Of course, you flip some coordinate system, or these vectors flip sign. So theoretically, one could say if parity was conserved, this is how under cobalt decay the distribution of electrons should be, and you can go and experimentally check this. And it was found that no, parity is not a symmetry for one of the fundamental interactions, this weak nuclear force. Okay, and again, I should mention this was a very, very important experiment. Okay. and the theorists who kind of alluded to this possibility was C.N. Yang and T.D. Lee, who won Nobel Prizes for this, but Dr. Wu was never recognized for this remarkable experiment. Okay, so this is something I think next weekend we're going to celebrate the International Women's Day. So this is something which we should again be cognizant about. Okay, that there are unrecognized women pioneers in science who have not been recognized sufficiently. Okay, so parity gone. Okay, this particle-antiparticle symmetry, which goes by the name of charge conjugation, gone. If you do simultaneously charge conjugation and parity, okay, then it looked like the physical laws seem to respect CP symmetry, charge conjugation and parity together. Okay, but you might guess where I'm going with this. But again, in another experiment by Cronin and Fitch, okay, this looks like what they essentially showed is that there is a particular bound state of quarks called the K plus or K minus meson. Okay, they're CP, this charge conjugation in tandem with parity violation. Okay, so even CP was not a good symmetry. Now, why is all this very important? We should be thankful that these symmetries were violated. You remember we were talking about this matter-antimatter symmetry? The only reason that we have more matter than antimatter was because charge conjugation symmetry was violated. CP was violated and so on. Otherwise, we would have a very, very dull universe. You and I wouldn't exist because for every electron, there would be exactly a positron. For every proton, there would be an antiproton. And what happens when particle and antiparticle meet each other? They just annihilate into pure energy. So it's precisely because of the violation of these symmetries, C and CP, along with some other ingredients, which goes by the name of Sakharov condition, which are not important, that there is at least a possibility, and which is confirmed by looking out the window, that there is more matter than antimatter. So we owe our existence to this violation of some of these fundamental symmetries. Okay, so this is one instance, for example, where symmetry violation actually, so all the beautiful architecture, music, patterns on a flowing lake or river, paintings, everything you have seen, those beautiful stars in the sky, we owe it all to this violation of these symmetries. Okay. There is also another aspect of symmetry breaking. I told you about violation of C and CP symmetries and so on. Okay, but there is also another aspect of symmetry breaking, which the young gentleman R's field. I said that there are all these particles,